okay, there was this derivation of the using the microcanonical ensemble, which I will skip. I mean, I think it's a beautiful application of the things that you have learned in mathematical physics course, but not so much. I mean, not the things we will be using in this semester in the rest of this course. And then we looked at the harmonic oscillator in the canonical ensemble. And it's basically a straightforward application. We looked at the low temperature limit, high temperature limit, and we also looked at the microcanonical ensemble, the same problem, and at least in one limit, at the high temperature limit, we also saw that they are equivalent. So any questions there? Today we will basically continue the applications of the canonical ensemble to different problems. So let's look at spin systems. This is relevant, for example, if you consider the electron or even the atom itself, it has a spin. The electron has a spin. If it is in an orbit, it can also have angular momentum. So these are basically moving charges, but moving charges has magnetic moment. If they have magnetic moment, they will interact with the magnetic field, and they will be magnetized. So we can use statistical physics also to study these systems. And if you have, let's say, an object with a magnetic moment mu, its Hamiltonian will be just minus mu dot p, whatever the magnetic moment is. So let's first try to study this problem. Again, we will assume, okay, so there are a couple of things we have to pay attention to. So if you look at any particle, it can be the electron, the atom, anything that has a magnetic moment, this will not be the whole Hamiltonian of the system. The whole Hamiltonian will be the Hamiltonian that describes the translations and the other external potentials, if there are any, plus there will be this Hamiltonian due to the presence of the magnetic field B. And in general, its microstates will have microstates corresponding to the translation. In classical physics, it's the position and the momentum. And it will also have microstates depending on its orientation with respect to the magnetic field. If you are doing quantum physics, whether the magnetic moment is pointing in the direction of P or in the opposite direction, or in classical physics, whatever the orientation of P, that also specifies your microstates. So the sum, if we are to calculate Z as a sum over all the microstates of e to power minus beta E, this will be a sum over microstates corresponding to motion and position of e to power minus beta. Let me just write E translation. And then there is another sum over the microstates due to orientation of mu. In fact, you can do this separation, for example, for an ideal gas with internal structure. There will be the microstate. The microstates will depend on the general translation and the position, and also it will have degrees of freedom corresponding to the internal degrees of freedom. So those two sums will also separate in general. Under a very good approximation, let's say. So the microstates due to the orientation of mu will be e to the power minus beta energy due to the external magnetic field. So we have the partition function separate into two. One due to the, let's say, the translational motion of these particles, and another one due to its magnetic properties. In this problem, we are looking at the magnetic properties. That's why I separate out the partition function due to its magnetic properties. Now, this Z translation for n particles, let's say, this will be Z1 to the n over n factorial. And if the magnetic properties do not interact with each other, if we ignore the interaction between, let's say, the spins of the electrons or the magnetic dipole moments of a given system of atoms, then ZB will be just Z1b to the power n. Now, there is no n factorial in this new z because the n factorial is already over here. That is one way of looking at it. Or another way of looking at it is, since we are looking at only the magnetic properties, I'm assuming that these magnetic dipole moments are pinned at their positions. So I can use their position to distinguish them. So they are distinguishable. If they are distinguishable, they won't have this Gibbs correction. Just like the harmonic oscillator case. The harmonic oscillator also didn't have this n factorial term. Here we also don't have that n factorial. Now, what will be the Hamiltonian? The energy of the system of a single particle, it will be minus mu times b times cosine theta. Depending on the orientation, the energy will change. And the partition function, well, I will drop the b. I will not look at the translational motion, translational degrees of freedom, or the position. I'm just looking at the orientation of the magnetic dipole moment. This will be a sum over all microstates of e to power minus or plus beta mu b cosine theta. And in this case, the microstates of a single particle will be given by a sum over all orientations of e to power beta mu b cosine theta. Now the question is, how can we carry out this sum over all the orientations? I say I have this magnetic dipole moment. Just imagine it like a vector pointing in some direction. Just like every position of my atom in the ideal gas gave me a different microstate. Now my magnetic field, let's just assume it's in the z direction. And every orientation of this magnetic dipole moment vector is a different microstate. So that's what I mean by a sum over all possible orientations. Of course, it's not actually a sum, because orientations, at least classically speaking, it takes continuous values. So we should somehow write it as an integral. So any guess what will be the integral? So how should I write this integral? Okay, so you came prepared. It is an integral over the solid angle. It's the solid angle that specifies the orientation of e to power beta mu b cosine theta. Now, you see the one obvious guess, no, not one one of the first guesses could have been just integrate over d theta d phi. No, that's not the correct one. We should also include the sine theta here. Theta goes from 0 to pi, phi goes from 0 to 2 pi of e to power beta mu b cosine theta. So now phi integral is trivial. It gives me 2 pi. Theta integral is also almost trivial because sine theta is the derivative of cosine theta. So that integral is e to the power beta mu b cosine theta with a minus sign divided by beta mu b. When theta goes from 0 to pi, or this is equal to 2 pi. When theta is equal to pi, cosine theta is minus 1. When theta is equal to 0, it is plus 1. 2 pi e to the power beta mu b minus e to the power minus beta mu b divided by beta mu b. So let me just call x as beta mu b. You see, this is dimensionless because mu b already has the units of energy. Beta is 1 over kT, which also has the inverse energy units. So x is a dimensionless quantity. So the partition function of just a single magnetic dipole within a magnetic field is given by 2 pi times sine hyperbolic of x. Now, what about the average energy of the system? Let's start with the average energy. This will be given by minus derivative with respect to beta of the logarithm of beta. No, sorry, logarithm of z. This will be the average energy, which will be minus derivative with respect to beta of sine hyperbolic x, the logarithm of sine hyperbolic x, which will be minus cosine hyperbolic x divided by sine hyperbolic x times derivative of x with respect to beta, which will be mu times b. Let me just write z is, this is z1, so z is z1 to the n. So here I have an overall n. N is the number of magnetic dipoles I have. Well, let's see, this is, well, we can look at various limits. In the low temperature limit, well, things should go to the ground state. The minimum energy configuration, well, the minimum energy configuration is when cosine theta is 1. So the energy of each one is minus mu b. So in the low energy limit, I should have the energy is equal to n times minus mu b. That is what I would expect. But remember, x is equal to beta mu b. So low temperature limit basically corresponds to x much, much larger than 1. Beta is very large at low temperature. So that is the definition of low temperature. Low temperature in this case means x is much, much larger than 1, or beta is kT is much, much less than mu b. So you see, in this problem, we have another characteristic energy scale, mu times b. That is what determines what is the low temperature and what is the high temperature. If the thermal energy is much less than the characteristic energy scale of the problem, then it's a low temperature limit. If the thermal energy is much higher than this characteristic energy scale, it's the high temperature limit. Well, let's say when x is very large, now let's look at this. U is equal to minus mu b times n. Well, cosine hyperbolic is e to the power x plus e to the power minus x divided by sine hyperbolic is e to the power x minus e to the power minus x. You see, if x is very large, the first term in the denominator, x is large, e to the power x is very large, and e to the power minus x is very small. So the first term, both in the numerator and denominator, it dominates. The second terms are negligible. So this just becomes minus n mu times b, as we expect at the low temperature limit. All the magnetic dipoles are aligned with the magnetic field. Each one has an energy minus mu b, and so the overall energy is minus mu b times n. We can ask the question, what about the specific heat at low temperatures? Well, if we would like to calculate the specific heat capacity, not the specific heat capacity at low temperatures, well, I need to find the next term in this expansion. Or it will be easier to take the derivative of u as a function of temp. Well, let's calculate it. Now the C as at a temperature T will be derivative of u with respect to temperature T. U is given by this expression over there, so this is equal to minus mu b times n, derivative with respect to x of cosine hyperbolic x divided by sine hyperbolic x times derivative of x with respect to t. Remember, x is mu b over kt. If I take the derivative with respect to t, I get a minus mu b divided by kt squared. So the heat capacity of this system is mu b over kt squared nk. Well, that derivative, the derivative of cosine hyperbolic, is sine hyperbolic so it's sine hyperbolic of x times 1 over sine hyperbolic of x, and plus cosine hyperbolic of x. Well, derivative of 1 over sine hyperbolic is minus cosine hyperbolic over sine hyperbolic squared and this is the heat capacity. Do you see a mistake somewhere? So u is minus the derivative of the logarithm of z with respect to beta. This is z. Z is 2 pi sine hyperbolic of x. Derivative of sine hyperbolic is cosine hyperbolic. So this is u. There's no problem there. Heat capacity is the derivative of u with respect to temperature. U is this one. This seems to be the answer. Well, the reason why I don't like this answer is, you see, cosine hyperbolic x over sine hyperbolic x is equal to e to power x. Oh, no, okay. No, e to power minus x divided by e to power x minus e to power x minus x. This is larger than 1. This is what I don't like about my answer. Heat capacity turns out to be negative. So that is what makes me think that I might have missed a sign somewhere. Oh, I don't see the sign.
Bir eksi var orada. Biraz yukarıda eksi mu.
Here.
O ama artı olur.
Well, this is minus, because you see I have a minus over here. And that minus makes sense because u at the low temperature limit is minus n times mu b. That is what I expect. Specific is the derivative with respect to temperature. There is this minus sign, which is this minus sign actually. And then I have the derivative of x with respect to t, which is, since x is 1 over t, there is another minus sign over there. If I take the derivative with respect to x of this term,
That's also alright.
that's also all right. So I don't see my sign. There should be a sign problem somewhere, but I don't see it where. Let me continue. Let's look at the high temperature limit. This is when x is much, much less than 1. Now what I expect at this time is, since we are at a very high temperature, the thermal motion will just randomize the orientation of the magnetic dipoles, so I would expect them to be randomly oriented. Some of them will have positive energy, some of them will have negative energy. So the average energy I expect it to go to 0. Well, let's see that this is u. This is the expression for general u. Well, cosine hyperbolic x over sine hyperbolic x. Sorry. I know where I made the mistake. Okay, let us go over the derivation. These are all wrong. Now let's look at over here, u, the z. Z is not 2 pi sine hyperbolic x. Z is 2 pi sine hyperbolic x over x. Let me divide by 2, multiply by 2, 4 pi sine hyperbolic x over x. This is my z. U is minus the derivative of the logarithm of z, so this is logarithm of sine hyperbolic x over x. Now I can look at various limits. So this will be minus n, derivative with respect to x. And remember, x is still mu beta over kt. If I take the derivative of x with respect to beta, it gives me a mu b of logarithm of sine hyperbolic x minus logarithm of x. Okay, this is my u, which is minus mu and b d over dx cosine hyperbolic x over sine hyperbolic x minus 1 over x. Now I can look at the low t limit. X is very large, u goes to minus mu and b. U goes to minus mu and b because cosine hyperbolic over sine hyperbolic x for x very large becomes 1. 1 over x goes to 0. I can calculate the heat capacity now. Heat capacity will be minus mu and b, derivative of u with respect to x times derivative of x with respect to t, minus mu and b, derivative of x with respect to t will be mu b over kt squared. Derivative of u with respect to, derivative with respect to x of not u, but cosine hyperbolic x divided by sine hyperbolic x minus 1 over x, okay, which will be sine hyperbolic x over sine hyperbolic x minus cosine hyperbolic x squared divided by sine hyperbolic x squared and plus 1 over x squared. Which is minus mu b over kt squared times nk times 1 over x squared minus 1 over sine hyperbolic square root of x. Here what I used is cosine hyperbolic squared x minus sine hyperbolic squared x is equal to 1. Just combine those two, the first two terms. Okay, this is the general expression. Whatever c is. Now, if I go to the limit of very small x, very large x, x is much, much larger than 1. So this becomes, as t goes to 0, x is becoming very large, 1 over x squared is negligible. So I have the second term only times e to the power minus 2x. Why? Because remember, sine divided by 4. Remember, sine hyperbolic x is equal to e to the power x minus e to the power minus x over 2. When x is very large, the first term dominates, the second term is negligible. So sine hyperbolic x is just e to the power x over 2 for very large x, and I end up having this e to the power minus 2x over 4. And as expected, as t goes to 0, heat capacity goes to 0, as is dictated by the third law of thermodynamics.
Can there be another sign mistake? Because one, we are taking the derivative of x with respect to t, there should be another minus sign, and in front of the equation there is also another minus sign. So it should be plus sign.
Yeah. Yes. No. You see, if it is a plus sign there, I get my negative heat capacity. There is another sign mistake somewhere. U is given by this expression, d by dx. Derivative of sine hyperbolic is cosine hyperbolic. Derivative of cosine hyperbolic is sine hyperbolic. Heat capacity is the derivative of u with respect to t. U has a minus sign. If I take the derivative of x with respect to t, I have an additional minus sign. When I take the derivative of u with respect to x only the square parentheses contribute, so, well, okay, there's another sign problem somewhere.
Hocam kosaydrometrik sinagogik türevini alınca aşağıdaki expression geldiğini ekleyebilir miyiz?
Well, let's see, d over dx of, I have cosine hyperbolic x divided by sine hyperbolic x, which is the derivative of the numerator, which is sine hyperbolic x, times the denominator, that's squared, minus the denominator, numerator, cosine hyperbolic x, times the derivative of the numerator, which is cosine, another cosine hyperbolic, divided by the numerator squared.
It should be minus 1 over sine hyperbolic, not 1 over.
Which is minus 1 over sine hyperbolic squared x, which is this minus sign. Anyway, I will correct my notes when I find the sign mistake. Let's continue if you like. Let's look at the high temperature. Well, high temperature means x is much, much less than 1 this time. Well, let's start with U. This is my U. Minus mu and B. Well, let's see. I need the expansion of cosine hyperbolic x divided by sine hyperbolic x for small x. This e to the power x, e to the power minus x, divided by e to the power x minus e to the power minus x. Let me just expand the first exponents up to x squared. 1 plus x squared over 2 plus 1 minus x plus x squared over 2 divided by 1 plus the difference. Well, in the numerator, the x's cancel. I have 1 plus x squared over 2 divided by, in the denominator, the 1's cancel, the x squared over 2's cancel over x. So this is 1 over x plus x over 2 plus higher order terms. This is my large temperature limit. Well, you see that this 1 over x minus 1 over x basically cancels this 1 over x over here. This 1 over x. So we are left with u is equal to minus mu m b times x over 2, which is equal to minus mu n b, mu b squared let me also have the n minus n mu b squared divided by 2 kT. I just wrote the expression of x explicitly. So energy goes to 0 at very high temperatures. So U is equal to so if I would plot as a function of temperature from 0 to, let's say this is plus infinity, the energy starts from minus mu n b, increases up to 0. Don't nod your head. You see, we have a problem here. Yes, I have such a system of magnetic dipoles. They can have both positive and also negative energies. But I see that no matter what I make the temperature, the energy I obtain is always less than 0. So how do I get positive energies? What happens if I create a system with positive energy? How can I do that? Well, let's go back and look at the expression of the energy. This is U. And let's say that I want to find the conditions under which U is positive. But if I want U to be positive, you see this term, this square parenthesis has to be negative. I want the first term to be negative. I mean, if the first term is not negative, is positive, well, yeah, I want the first term to be negative. Let me put it that way. Well, cosine hyperbolic x, which is e to power x plus e to power minus x over 2, this is always positive. So I want sine hyperbolic x to be negative. And remember, sine hyperbolic x is e to power x minus e to power minus x over 2. For this to be negative, I need to have x less than 0. Only if x is less than 0, I might have u positive. I should still check that if x is negative, the cosine hyperbolic divided by sine hyperbolic will be negative, but 1 over x will be positive, but still the square parenthesis, if x is negative, will be negative, if x is negative. But remember what x is. X is equal to mu b divided by kt. If this is negative, then T should be negative. So now we have our system of negative temperatures. If somehow we can create a system of magnetic moments which has positive energy, it corresponds to negative temperatures. Yes, if you remember your first exercises, there was a question claiming that negative temperatures are hotter than positive temperatures, meaning that energy flows to positive temperatures. So here, our example, negative temperature states are states that have higher energy. They have energy higher than 0. Positive temperature states will have negative energy. You see, this will behave like this. This is plus mu b n from minus infinity to 0. Positive energy states have higher energy. Sorry, negative temperature states have higher energy. So energy still flows from high energy states to low temperature low energy states. Of course, can we create such a system? That's a different issue. And in fact, we can. You see, what we want? We want a system that's in thermal equilibrium. That should be long-lived enough. So we want to find a system of magnetic dipoles, which, even if they have a positive energy, they will live long enough so that we can make measurements, so that they will thermalize. But if we have a high temperatures, high energy system, it can just get rid of the energy. It can transfer the energy to other degrees of freedom. So we want a system of magnetic dipoles that do not, okay, before that, by the way, Why do you think temperature has to be positive? What's the reason for temperature to be positive?
Didn't we define it so?
Hmm?
Didn't we define it so?
No, I just defined it to be, at least up to this time, I defined the temperature to be the derivative of entropy with respect to energy. And then intuitively, what we expect is the entropy should increase as the energy increases.
Actually, from the third law, didn't we define that?
No. The third law basically tells me that at the lowest possible temperature, let me rephrase it that way, at the lowest possible temperature, entropy is 0. But you see, negative temperatures are not the lowest possible. They are above infinite temperatures, in a sense, in the sense that their energy is higher. Now, the reason why the temperature needs to be positive, let's say, is, let's look at the partition function. Sum over all microstates. We want this sum to be convergent. This sum should converge. If you put a system in a finite volume, this should converge.
If T is positive.
If
Temperature is positive.
well, let's see. If, there's another if before that. If energy is not bounded from above, if I have microstates of arbitrarily large energy, the condition for this sum to converge is that beta should be positive. But the first if is important. The energy should be unbounded from above. In general, that is the case because the translational motion, translational energy is, well, the kinetic energy is unbounded from above. It can take arbitrarily large values. But now we are looking only at spins. We are ignoring the translational degrees of freedom. And hence, energy is not unbounded from above. It's bounded from above. The maximum energy that my spins can have is n times mu b. So for such a system, when the energy is not bounded, is bounded from above, the temperature can be negative. Okay, how can we create such a system? Well, we can create such a system only if we can separate the translational degrees of freedom with this magnetic properties. That if the interaction between the translational degrees of freedom and spin degrees of freedom are weak enough, then we can create such systems. And in fact, nuclear magnetic systems are such systems. Nuclear magnetic moment doesn't interact with the other degrees of freedom strongly. The interaction is quite weak since because the interaction is basically proportional to 1 over the mass of the nucleus. The mass of the nucleus is large, so the nuclear spin doesn't interact with the other degrees of freedom. So you can just separate your system based on their degrees of freedom. And then you have a magnetic degrees of freedom separated from the other degrees of freedom. And you just polarize the magnetic moments first. You put your system in a large magnetic field, wait long enough so that all the magnetic moments will be aligned with your magnetic field. Then you suddenly reverse the magnetic field, the external magnetic field. Well, if you reverse the magnetic field suddenly, the nuclear magnetic spins will not be able to flip. Since the interaction, you see, the flipping should conserve energy, so the energy should transfer somewhere else. But the interaction with the nuclear magnetic degrees of freedom and other degrees of freedom are weak, so that transfer of energy takes a long amount of time. So at least during that time, you have created a system of negative temperatures. Of course, there are the translational degrees of freedom. You see, up to this moment when we separated our systems, we have been thinking about, okay, I have a group of particles over here at some energy, another group of particles over here with some other energy. But I mean, the separation need not be in terms of particles. We can also separate our degrees of freedom. We have a subsystem consists of translational degrees of freedom of all my atoms. Another subsystem consisting of all the nuclear magnetic moment degrees of freedom. These two systems will interact, but the interaction will be weak. When you flip the magnetic moment after fully polarized or almost fully polarizing the magnetic, nuclear magnetic moments, you will have two systems, one at positive temperature, which involve the translational degrees of freedom, etc. It didn't change when you flip the magnetic moment. The other one is the nuclear properties. That has a negative temperature now. These two systems have a weak but still a non-zero interaction. So eventually, negative temperature system will transfer its energy to the positive temperature system, meaning that magnetic moments will start flipping. And then you end up having to, again, your system as a whole will be at an equilibrium at a positive temperature.
Isn't this cheating?
Why?
The negative temperature systems, we can only observe them in a certain time interval. For a certain time interval, panels, correct?
Mm-hmm.
We omit some part of the U and consider only spin states at the translation.
Yeah, so I'm basically doing a separation. It's here. I'm just writing this sum as two separate sums. I have two beta terms. They don't have to be equal. Nothing tells me that they have to be equal. In fact, after I flip, my spins are still in thermal equilibrium, but with a negative temperature. In the second term, beta is a negative. In the first term, beta is positive. But you did bring down another aspect during the duration of some period. You see, we didn't discuss in too much detail what do we mean by equilibrium. For example, do you think that this classroom, the air in this classroom is in thermal equilibrium or not? If I'm asking, probably the answer is yes or no.
For some time interval, yes.
Yeah, I mean, if I look at this classroom, the atmosphere in this classroom, for, I don't know, 10 minutes, it's in equilibrium, nothing will change. Of course, I should also avoid the region near your bodies because your body is at a higher temperature. But if I look at this, the atmosphere in this classroom for, I don't know, for a week, it's not in equilibrium. It changes, at least these days, between now probably something around 22, 24 degrees. At night, probably it becomes something around 10 degrees. It's not in equilibrium. So being in equilibrium itself can also depends on time, in the sense of what is the time interval you are observing your system. So here, yes, I do have my spin systems. Its interaction, the degree interaction of these nuclear magnetic spins with the other degrees of freedom will be weak. So the thermalization time between the spin degrees of freedom and other degrees of freedom will be long, maybe hours. So if you make an observation that lasts a few seconds, during that a few seconds, that spin degrees of freedom are in equilibrium at a negative temperature. So in that sense, I'm not really cheating. All equilibriums are kind of time dependent. Yes, eventually the universe will disappear. So if you wait for that long, nothing is in equilibrium.
Can I say that these things happen in the Stern-Gerlach experiment, for example?
No, not in the Stern-Gerlach experiment. You just send electrons one by one. These are, I mean, this doesn't happen for the electron spins. This happens for nuclear spins because their interaction with other degrees of freedom is really weak. But of course, you need to have your sample, put it in a huge magnetic field, and then flip the magnetic direction of the magnetic field. Now, it might be easier to flip your sample. Other questions? Okay, so let's give a 10 minutes break and then we will continue.